Okay, we'll take our seats, please. We've got quite a full day. So, welcome to Leeds. Welcome to the DART final workshop. Thanks so much for coming up here from wherever you come from. It's great to see some old friends and also some new faces. We're sort of doing a round-robin introduction, but that's going to take quite a bit of time to do that. So, I'm just going to introduce myself, Tony Cohn, PI of the project to begin with. All the speakers will introduce themselves as they get through. If you have questions for the floor, please introduce yourself and where you come from or what your interest So I'm going to start off with just a few minutes of introduction to the whole project and the day. Then Ange will take over with a long overview of what it is we've done, and that will act as an introduction to the student presentations. So, also just to point out, we have Elaine here who is going to be videoing and transcribing things, so we have a record of all the interesting things that everybody's going to say. Don't let that make you nervous, but this is an important enough event that we really want to make sure we don't miss anything from the benefit of your interaction with us. So the format of the day is that in a few minutes, then we've got the three presentations from Dan, Birmingham, Rob from Bradford, and David from Leeds. Then Anne's going to do a short production activity together. We're going to say something about modeling the data. I'm going to say a few words about what we might do with all this data, and then we're going to open up for a discussion until lunchtime. We're going to try not to take questions to begin with. We're going to try to reserve all questions. So I know you'll be itching to ask people. Just make a note and then come back at that point at 12 o'clock, okay? And then we can bring it all together. I believe that Chris is going to be trying to keep us all to time today. Did you agree Chris on that?
We did agree on that. I do have a whistle for you.
In the afternoon, we then move to the wider scope outside the DART project and how this things interact with the community. And we'll have more introduction to that later. So we hope to wrap up at 4:30. So about 4 years ago, we put in this project in response to an AHRC Arts and Planners Research Council and the EPSRC Engineering and Physical Science Research Council bid for science and cultural heritage. And it was very open. You could do anything. There were people who got funded to build electronic noses, who do visualization of bits of archaeology, of old buildings. It's all kinds of different things got funded. This was the only one that was really funded of this kind of archaeological bent in terms of remote sensing. And what we were interested in doing, as you say here, was to really get a better understanding of the operation of stress parts in fields, which are caused by arid residues. And this was to try to understand the science, but also to try to then influence how the community goes forward as a result of that better understanding. And so that we've now kind of reached that point where we've got all the data, we're trying to understand it, and we want to think about how we're going to make use of what it is we've learned. So there's the kind of formal side of the presentations that are going to be coming up from the various speakers, but also, I mean, there's going to be coffee breaks, there's going to be lunch. Please interact, please just have full discussions in discussions. The PhDs are kind of nearly finishing, but they're going to be going out into the community, I hope, and taking their expertise from DART to there. So I think, was this the point you were going to take?
I think this is all hands over.
Yes. So I'll be talking again later, but I'll let Ant go forward now.
Okay, so I'm going to give you a whistle-stop overview of the project and its inception. We have a large consortium, including academic investigators, consultants who can provide us with a whole range of insights to new advances and new techniques, a number of heritage professionals and industry professionals. Pointed out both Dave Cowley and Roger Palmer, as I did from the first workshop, because without their support this project wouldn't have happened. We have our 4 PhD students, 3 through DART, 1 through a departmental bursary at Birmingham. These are very original projects. These have changed a little bit, but I'll let them tell you exactly how. We have a whole range of different people who made this work. I don't expect you to read these, and I'm not going to go through each of these. These slides are online, so you can go back and you can refer to them. But we've had a number of different industry involvements I do want to bring out. Van Volt, Allied Associates, Leica Geophysics, and Hooksy have all supplied equipment and support, and so I do want to say thank you to all of them. And we've had a number of other academic collaborations, and I haven't got David Jordan in here, so sorry, David.
I'm late.
There you are. So, you know, from the outset, we've been a project that's trying to be inclusive, not just within the academic arena, but throughout the whole stakeholder community. So, a quick project overview. We've been focusing on contrast identification, the physical, chemical, and biological variations that lead to the formation of features that we want to detect with our equipment, which we can do directly or by proxy. It's not well understood. Dart has been focused on trying to understand those a little bit better and to put them within their environmental context. To quickly go through to this side, this is looking at aerial prospection, so you can look at variations in crop canopy height. You can look at differences in crop colour. You can look at variations or micro variations in the topography, and you can look at variations in soil colour. Equally, you can look at variations in thermal effect, and you have these lag effects over time. So the way that we can detect these contrasts varies depending if we're doing it directly or by proxy, and the kind of sensors that we're using to detect those elements. We have a number of different work packages. Again, you can go back and look at this in detail. We've achieved most of them. We have some question marks against others. Again, this workshop is an opportunity to look at some of those question marks in a little bit more detail. We have a number of milestones. Similar thing. We've achieved most of them. We have question marks against some. And again, this workshop will help move that forward. Communication infrastructure. We had a website, amazing project with a website. But we tried to do this in a way which aggregated our information. We shared stuff internally. We had an internal Dropbox-esque component. We had a whole heap of structured email lists. I'll talk about the open science bits later on. But we also deposited all of our data into public environments. So videos on YouTube, documents on Script, bibliography elements on Mendeley, presentations on SlideShare, photographs on Flickr, general conversations on Twitter. Because these are open, with open APIs, we can actually access them and aggregate them through our website. So our website became media rich because we were linking it directly through to the media, which we were putting up as part and parcel of the project, which is nice. This is where I'm going to spend most of my time. This goes into the science and broadly about what it was we were doing. We had two sites, one in Diddington in Cambridgeshire and one at Park Hill in Cirencester. Diddington site, there's Diddington in the south, you've got the A1 here, you've got a loam area to the east of the A1, you've got a clay area to the west of the A1. We did some preliminary geophysics. Well, essentially what we wanted to do at these sites was find locations where we had both heavy soils and free draining soils. So logistically, we could visit multiple sites in one day and look at those major differences between the heavy clays, which are difficult to detect things on, and the loamy free draining soils, which are easier to find at least crop marks and other anomalies on. We did initial magnetometry surveys, identified areas which we'd like to go in, did initial coring so we could find out, at least begin to characterise the features that were there. Similarly, over in the clay area, sorry Rob, this is probably not stretching the way that you'd like it to be. So that's what you do when you get cross-disciplinary work. This is the area of Park Hill, and again you've got your clay area over here and your loam area down here. This is a field called Cherry Copse. Lovely, lovely Roman villa somewhere down here, and lots of very, very nice field systems. So that's where we did our coring, and that was where we wanted to put our trench. More about that later. And this is Quarry Field. Not very exciting field boundary, but is essentially going to show the processes. So you've got the rig and furrow, you've got the old field running across there. The general framework was to dig a hole, insert temperature, soil moisture sensors, both in the archaeological feature and outside the archaeological feature. Oh, this is a ditch. Close to that, because we've got some IMCO TDR probes that have been lent to us by Van Volt, and we also bought a companion set. We could do a comparison between those probes and the information from Birmingham's TDR. Sorry, the jargon will be explained in a bit more detail. We had a geophysics survey area, so on a monthly basis we could undertake geophysics close to the areas where we're doing our monitoring. And then we'd have a spectroradiometry area where we essentially measure electromagnetic variations across the spectrum on translates across the area. On top of that, we'll be collecting both vertical aerial photographs, hyperspectral imaging, and full waveform and discrete return LiDAR. So we're getting multi-temporal collection of both in situ data about what's going on at the feature level, all the way towards how that's being impacting rather on crop growth and changes over time. Okay, so at the top we have our as designed for the probe installation. So we're looking at getting both TDR, time domain reflectometry, from which we proxy our soil moisture, and temperature probes going down the archaeological feature, and then further probes outside the archaeology with a lateral offset as well, so we can look to see if there's any variation, if the archaeology itself acts as a sponge effect, changing the localized soil moisture or temperature characteristics. The IMCO probe, because it's a core-based, a core-driven probe, you just put your core in, put your probe in, and then log it, and it telemeters out there. So that's the as design, and this is an example of the as built. See again a bit more of that later on. For the well-draining soils, we had 8 and 8. For the clay soils, we had 16 and 16. So we could characterise the clay in a little bit more detail. And so we resulted in something like this. Again, you've got your ditch feature running through, your excavation area, your TDR and temperature probes, your geophysics area, and we end up collecting a whole heap of different data at different temporal intervals. Okay, so here's the general picture of the UK. There's Cambridge, there's Harn Hill, there's Diddington, there's Harn Hill. We've got a split between the drier area in Cambridgeshire and the wetter area in Cirencester. And if we go down into each one, okay, we're back into Diddington again here. So you can see it's an arable environment. And this is our clay field. So we had our geophysics area. This is the place where we had our IMCO probes. This is where the excavation was. These are where the boxes are for the TDR. This is where David did his spectroradiometry readings. Okay, then. And this is our section profile. So you can see the ditch, you can see the areas where we took out the samples. One thing I didn't say, actually, in the previous slides, which I should have done, samples are taken away for laboratory analysis, where we did particle size, we did loss and ignition, and we did basically, that's exciting, a whole raft of laboratory measurements. Okay, down at the pasture field, this is on the free draining area in Diddington. We had our initial area of excavation and installation, some are set up here in 2013. This is the geophysics area in 2013. We did a characterization trench in here and took more samples out. So we could actually take samples directly over the area where Rob had been taking his geophysical measurements. Interestingly enough, our section profiles, which are very clear here, are somewhat different here, even though it's, it's about 10 metres away from the original trench. And so one of our assumptions was that everything would be similar, quite close by, slightly blown out of the water. This is Harn Hill. This is quarry field here. Again, similar setup, geophysics area, spectroradiometry, trench. We also have, we undertook a thermal experiment in this area, so we did diurnal measurements over a 4-day period Here's our scaffolding, and here are the areas where we took those thermal experimentation, and that was with John Wells at the back. Section, and finally this is cherry tops. Now you'll notice, that we were going to be going in down here. The villa area was scheduled a week before we went into excavation. Lots of telephone calls were held, and we decided that unless we wanted to basically write lots of paperwork to go in on a monthly basis to undertake geophysics, it was just a nightmare. But we shifted over to an old field boundary here. So, same as we've got the excavation area, geophysics area, and we also did our film experiment here on spectroradiometry. Okay. And quickly into the achievements. We've achieved a lot, so much you can't see. We can zoom in, but again, these are all online, so if you want to go into a little bit more detail, we have lots of data. Most of it is available online in a repository. I will be showing this later on. We've attended lots of conferences and gone to workshops and such things. We have publications and presentations, there will be more. And we've done other stuff too, particularly trying to improve impact in media and in public profile. Okay, that's us. And whistle stop tour done. This will all be available as a mind map. I will send links through to everybody at the end of this event. If you're happy, I will send delegate details around to everybody. If you are not happy in doing that, find me and I'll not do it. Actually, I'm well on time as well.
Goodness me. Does that mean I have to tap dance for 10 minutes or something? Because we're ahead of schedule. I've actually just gone and Googled DART meeting 2013 and just to try and find out what the programme was, because I didn't catch it on the first slide. And actually it came back, one of the first things was DART's World Supremacy 2013. Am I at the right meeting? We obviously do have a few minutes to perhaps quiz Anton on some of those issues that he just raised. I don't know, perhaps it seems like we perhaps should move on a little bit and hear from the PhD students, because actually they will flesh out a lot of the issues that Anton already shown. Is that okay?
That's fine by me.
In that case, let's just bash straight on. Dan, are you up next?
I think so.
You are? Excellent. Good.
Is that good?
We've got three students who will be talking today. Obviously, they're being linked via this particular project, though there are three different institutions. Dan is in civil engineering in Birmingham.
Hi, just to introduce myself, I'm Dan. I'm looking at the soil, particularly soil and electromagnetic radiation response. Just as a bit of a sort of thing to limit expectations, if you like, this is very much kind of work in progress at the moment. So by all means, I don't have all the answers at the moment, but I'll just show you some of the. So I'll talk about what I've been doing, how our research is developing, and hopefully we'll get some answers one day. The final and definite. So why electromagnetic radiation? Well, DART is essentially focused on improving the detection of archaeological sites, both using remote sensing techniques and geophysical techniques, all of which really rely, or certainly a lot of these relies to a greater or lesser extent on the reflection of electromagnetic radiation. Now, whether that be ground penetrating radar, or your visible spectrum, or your low frequency electromagnetic sling ground systems, EM38 mini explorer and things. But the thing is, they've all got different operating frequencies, which is a bit of a pain. So just a bit of physics, which I'll just gloss over for people that aren't physicists. Essentially, reflection of any applied signal proportional to the incident signal, a reflection coefficient, which is defined from the impedance, which you can calculate from these things here. Essentially, your impedance relies on three main things. You've got your magnetic permeability, you've got your bulk electrical conductivity, well, your electrical conductivity, and your dielectric permittivity. Generally speaking, we tend to consider the magnetic response not to change too much on a seasonal basis. I don't think anyone's properly proved it, but I think we have an inkling it doesn't change too much. So, but the other two do change. Therefore, recording them is obviously important. The other thing they do is they affect the speed and the attenuation of electromagnetic radiation. Now, the thing is, these are dependent on the soil conditions, which change throughout the year and obviously seasonally, following things. So what I basically had to do is come up with a way of instrumenting the sites to monitor this on a sort of a regular basis, sort of like over the whole year. And what we decided to do is we decided to put in time domain reflectometry probes, the legendary TDR probes that Ant was talking about. I'll just give you a quick rundown of how they actually work. Essentially, what they consist of is they consist of a pulse generator, a timing circuit, and an oscilloscope, and a coaxial transmission line. And what we do is we send that EM pulse down the coaxial thing to the probe. You can see here, and it ends up here. At this point, because you've got an impedance change at the start of the probe and an impedance change at the end, you can identify these points. So you start here and you end here, and the time between those gives you a travel time, which you can use to determine the dielectric permittivity. The other thing we can do is do an analysis of how much of the energy is lost. And if we leave that for a long enough time, it should roughly approximate DC conductivity, so we can measure that as well, which is an opportunity. So we instrumented the ground with these, and what they do is they measure from each of those probes every hour, and they take one for relative dielectric permittivity and one for bulk electrical conductivity. The dielectric permittivity can then be used theoretically to calculate moisture content, because if you use a mixing model or an empirical model, because water is by far got the highest permittivity of the things in the soil. You know, you've got air, you've got solid particles, you've got organic matter. Air's roughly 1, solid particles are roughly 3 to 5, and organic matter also about 3 to 5. But water's 80, so it responds strongest to changes in water content, which brings us on to what affects permittivity and conductivity. So you've got water content, which variations obviously based on rainfall and climatic conditions. But as well as just having differences in water content, there's also a difference in how water behaves when it's in the soil, because it has interactions with soil particles. So it binds itself to the surface, which adds an additional complication to what we're doing with our models and things like that. Basically, contrast in soil water content tend to be affected by differences in either the maximum storage capacity of the soil, how much water can it hold when it's saturated, which is based on its particle size and things like that, and also differences in infiltration. You know, does it infiltrate faster through the ditch? Can it not infiltrate through the natural whatever? So it's worth looking at both of those things. So you've got storage, which show as a higher reading for a long period of time, sort of thing, and storing more water at that point. And you've got infiltration, which will show as a faster rise after a rainfall event. And we can look at both of those. The other things that affect our response, the frequency of the signal, which depends on the instrument we're using. Now with TDR, we're firing a broadband pulse, so it's got kind of like a range of frequencies carried within that pulse. So we can only ever approximate it at whatever the effective frequency is, which is quite difficult to define, which is a bit of a weakness of the TDR method. And as you can see here, at different frequency ranges, different types of polarization mechanism are taking place, and different loss mechanisms are taking place. So we've got a real part here and an imaginary part here. So these are essentially losses, and these are essentially storage of energy. But you can see even within the TDR range, there's a big variation. And what that effective frequency is actually sometimes very difficult to define, so it's worth knowing about. The other thing that affects permittivity and conductivity is soil temperature, which obviously varies on both the seasonal and the diurnal pattern. Temperature tends to affect the behaviour of the water because you've got higher ion mobility, which increases the conductivity. It also affects the thickness of the bound water layer. And the relationship with temperature is by no means simple necessarily, and it probably depends on the type of soil you've got, how big its surface area is, things like that. And to a greater or lesser extent, if you go to the literature and read what effect temperature has on conductivity and permittivity, the extent of its importance is very much debatable. Everyone agrees it has an influence, but whether it's a strong influence or not so strong influence, you know, worth checking out. So I'm going to show you some data. So Anne's already shown you this. This is Diddington Clayfield, which is one of our sites there. As the name suggests, this is one of our heavy soils, our ones that don't drain well, theoretically don't drain well. So you can see where we put the probe. So we've got essentially 16 in the ditch here. And what we do, I tend to average them by depth at the moment. One of the things I've done is I've taken the potential of evapotranspiration away from the rainfall. So you can see periods of drying, because it didn't make much sense when I plotted just against rainfall. So I basically took it away because it's useful to be able to see the bits where it's almost not raining. So you can see here there's a big drop. Basically, the first thing to say about this is actually we didn't realise it at the time, but actually this took a long time to settle down. So you can see this bit here is all flat, except on the very top. And if we go down, it's flat for even longer. And essentially, it's not until you get this first wetting front that we really start to respond to anything. I think a lot of that is the installation of the probes, in that we dug a ditch and we left the ditch open. We put the probes in the side of the space and we dried it out. So we took a lot of the residual moisture content out. So the hydraulic conductivity was like really low at that point. It really struggled to transmit water until that actually happens. And once that happens, it seems to settle down a bit, and you actually start seeing some kind of response. But if we go back to, you see that most of the response is near the surface, obviously. And lower down, it doesn't respond except sort of after a period of quite extreme drying. So if there's a lot of drying, sometimes it responds lower down. But I think the main thing to take away from this is it seems to be holding the water mainly towards the bottom of the ditch here, but there isn't a huge difference at many points after everything's settled down. The other things to say is the archaeology seems to settle down a little bit faster. As you can see, this doesn't have that big initial wetting until much later. So it seems, at least in the first instance, it was a lot quicker to settle through that. To look at the conductivity, you see actually fairly similar trends on the whole. That it seems to be mainly affecting the near surface. Again, we've got that problem of settling. The only thing I can really say is essentially the difference is again on the bottom where the moisture seems to be being held to a greater or less extent. And these are sort of like almost, I think these are slightly at the bottom of the ditch, sort of the natural below. I say natural is the wrong word. We've got kind of an archaeology surrounding soil matrix, I think I'm calling it for the time being, whatever it is. And you can see even when this bit's flat on permittivity. So this is fairly flat, but on this one, even down the bottom, there's a slight curve here, which suggests there's a slight temperature response there as well. So I plotted everything: electrical conductivity, apparent permittivity, and then the colour according to temperature. And you can see there's almost no relationship. The relationship between temperature and permittivity seems pretty small, but the relationship between temperature and conductivity is much higher, particularly when the soil's wet. You can see that's from the archaeological tools, same site. So So yeah, the other thing we put in was temperature probes, which we measure every half hour. And you can see nothing you really wouldn't expect here. In fact, we're missing some data here from where I couldn't get the logger working initially. But essentially, it tracks the air temperature, and there's definite heating up and cooling down. So the only other thing to say is the archaeology response to a slightly greater extent here, and here tends to be slightly lower here and slightly higher here, which probably not unexpected. Go down, and it drops off at depth. One of those sites. This is the other side of it. This is dipping into pasture field. This is the well draining site over at Billington. So you can see this was mainly sort of sands and gravels, digital there. Again, you've got a similar pattern. The only thing I can really say about this is there's a rather interesting thing going on here, which I don't fully understand, but I actually think there's a point where the water table comes up. That'll be the one. I don't quite know what's going on with this. I'm still investigating that. But it's a bit odd. But again, it takes a surprisingly long time to settle and start responding normally. Same with the conductivity, really. But again, the main differences seem to be sort of like 0.81 metre. They're down the bottom of the ditch. It seems to be where it holds the greatest difference, which we'd kind of expect because the topsoil is kind of fairly. I mean, this side wasn't ploughed, but the topsoil and there's this sort of capping layer here, which seemed to go right the way across the site. But I don't know whether we ever decided quite what it was, but it's quite fine greenish material. Again, I've done this again. You can see this never gets as high relativity because it can't hold as much moisture, but the patterns are pretty similar. Same with the temperature, except there seems to be very, very little difference between your archaeology and your swelling soil. Here, there seems to be very little difference at all. So the other thing we can do is obviously look at infiltration, which I've been doing. So one of the things I've noticed is that there's different types of infiltration. So you'd expect our coarse grain soils to redistribute in this manner. So if you take that as time 0 after it rains, and then time 1 and time 2 coming on afterwards, you tend to find it goes down as a sort of like continuum. Whereas on a fine grain soil or quite shallow depths, you tend to find it desaturates the surface as it goes down. Now if we go back to those other slides, you'll see that both of them seem to be responding more like fine grain soil, which is a bit odd. So one of the things I've been playing with at the moment is trying to work out what the lag is between it raining. So I've done this on loads of events, but this is something called autocorrelation, which essentially correlates things with the time lag. So you can see at what point it responds. So you can see here, obviously, this is an hour. It's quite thin, but as you go down, it takes less time. But you can see there's a slightly faster within the archaeology. That's a bit of a mess, but yeah, by the time you get down there, there's no real pattern at all. Same activity, essentially, obviously. The other thing we've had the opportunity to do, because Vandal generously lent us one of the IMCO probes, is compare our TDRs, which are measuring permittivity and conductivity, with their IMCO probes, which measure moisture content from the travel time and conductivity, or some kind of measure of conductivity anyway. So what we did, we required a a polynomial from them which turns their moisture content back into permittivity because everything's done in build. And it gives us the opportunity to plot them against each other. So you can see this is a small period, but it's not atypical. You can see that basically their probes tend to respond to it, our probes tend also respond to it. It's there, but there's a difference in absolute values, which is interesting. But essentially the trends aren't dissimilar. And we did the same thing with conductivity. Now, conductivity is an interesting one because mine are all down here, and theirs are all up here. So they're measuring in millisiemens apparently, and there's vastly higher. So if you plot it on a logarithmic scale, you can see it's still following the same trends. But there's a difference in the absolute value, and it's probably something to do with the way they calculate conductivity. But we're not really sure how they're doing it. But I think it's indicative of trends, but I'm not sure about the absolute values. So the main advantages of the IMCO probes are obviously they're much faster and easier to install because they go in as a core rather than having to dig a trench and stick probes in. They don't create any soil disturbance. And they're good at identifying trends in both volumetric moisture content and bulk electrical conductivity. And they come ready made with a telemetry system. There's a much simpler interface because you don't have to process your own data. But the disadvantage of them, I would say, is that they have a pretty undefined measurement volume with it being the plastic tube. And that plastic tube and electrode coating makes the conductivity determination a little bit problematic in terms of absolute values. And the other thing is the model that's built into them doesn't necessarily fit all soils, and you might have to empirically calibrate them in order to overcome any problems in that regard. I think what you've got to ask yourself when you're installing anything is what's the overall aim here? If tracking the relative changes is what you want, they're a good solution, I think. So what have I learned? The greatest difference seems to be water held at the bottom of the ditch, I've shown you. The magnitude of the difference is greater in the coarse grain soils, which won't surprise anyone. Infiltration tends not to affect below the top 30 to 40 centimetres on either side that I've looked at so far, except in case of extreme drying beforehand. Temperature has a minor role in permittivity, but a large role on BEC, particularly at saturation. I think a lot of what I've learned is actually how to monitor soil properties long term, because ultimately I lost a lot of these sensors. Flooding, animal damage, and obviously that settling issue I showed you that maybe you need to install them either a long time before or wet the probes in. And my work's still ongoing, so I've got the two sites at the RAC and Cyrus to look at, and I need to start linking this behaviour to some of the soil lab work, which Laura's doing at the moment, and make some conclusions based on that and better understand what's going on. But I'm still looking at things. So just to say thank you to a few people, I've got to say thank you to Van Dal, obviously, for lending us the IMCO probes. I'd also like to thank Uzi Electronics for lending us the radar. We did do a couple of radar surveys which I haven't looked at or anything, but it's kind of influenced the equipment. And also just a thanks to some of the other people at the project.
We'll keep on moving through, and we'll take the discussions at the end, as Dan said. So next on we have Rob Fry, who's just refreshing himself. Rob's from University of Bradford, and will tell us about some of the geophysical measurements that.
Yes, I'm Robert Fry from the University of Bradford. I basically look at the sort of more geophysical above-ground measurements that we've taken throughout the project. Specifically on the issue of resistivity and electrical imaging, and centred around the idea of a seasonality problem with investigating different soils. The seasonality problem with persistence is well known within the community. We know that at certain points in the year we can see a ditch feature with our resistance measurements, and at certain points in the year we can't. There has been a few studies taken which have mainly looked at big ditches on easy draining soils, and they've tended to come to a conclusion that month X is the best month to do a resistivity survey. This to me seemed like an extremely simplified overview of a problem that's much more complicated than that. And with DART we have the opportunity to look at multiple ditches and much more common garden, small ditches on both our free draining and our very difficult clay soils. An example of the difficulty with the problem is the current English Heritage Guidelines, which helpfully suggests that the best time to do a survey is when moisture contrasts are at the most accentuated, which is very true, but not very helpful in practical terms. So hopefully in this presentation I will introduce to you some of the data we've collected, introduce a new methodology I've come up with quantifying how we can look at the actual response we're getting from our ditches. I'll then look briefly at some weather estimates to see how the contrast factors with our earth resistance measurements correlate with the weather. And then I'll try and investigate whether we can specifically look at different soils within our ditches to see if we can fully understand why we're getting a response or not. So we did a resistance survey over our sites. So we're using this sort of Zimmer frame device. We actually took a multiplex survey, which means we increased the spacing of our electrical probes, which essentially gives us slightly increased volumes of soil to look at each time. And this is basically a page of all our data we've collected, simplified into box and whisker graphs. It's maybe not the most useful slide to have other information there, but the biggest thing to take away is the idea of seasonality. This is just our data, this isn't the digital, this is just the whole data set. And we can see that we're getting a very non-seasonal relationship. If we zoom into, say, this section here, that's our entire fieldwork season. This is the resistivity of the data from June 2011, and that's the resistivity of the data in June 2012. We get complete different contrasts in the same month, and different apparent resistivity measurements as well. So we're not seeing a seasonal data set. In fact, it's basically peaked in July 2011, and the resistivity basically just dropped across the site throughout the whole survey season. Granted, it wasn't a very seasonal fieldwork season. So this is some grayscales of our data. Each square is a month of survey. We've got our high hill sites up here, Eddington sites down here, free draining and clay. What's hopefully quite obvious straight away is that our free draining soils produce a nice ditch anomaly, this negative white anomaly going down through the data set every single month, nice and clearly. At pasture field we have this sort of more triangular feature because it's actually two ditches coming together, and this is the junction of those ditches. Again, we can see that essentially every month. At Quarry Field, our clay site, we're seeing a ditch every now and then, and some months we're not really identifying it that well. Interesting as well is that it's a positive feature. It's actually coming up as a black feature, so a positive, a high resistance anomaly. Dinnington Clayfield, I thought we'd never see the ditch, but in our last month, we saw a nice negative anomaly coming through to be our ditch feature, which gave me lots of joy. Seems to have a bit of an issue there. So basically I looked at the data as if I was doing a commercial geophysics survey, looking at high or low anomalies or looking for archaeological features. And I'm actually highlighting the ditch in purple on these ones. So it's quite graphically shows the ditch coming through in all months in our free draining soils. In Quarry Field, it came through about 60% of the time, and if this wasn't corrupted, you'd see a nice ditch there as well. So only 1 month at Dinnington Clayfield do we really see it in that data set anyway. So going back to when we see the ditch every month, That's very useful, but what's also very useful is what's the magnitude of that anomaly? How can we quantify how that anomaly might change month on month on month? And also, in our hard-to-find regions, again, is there sort of some sort of way of quantifying how we can see that anomaly compared to the other months? And one way I came up with calculating a new contrast factor was to use a two-method sort of algorithm, I guess you'd call it. First is a detection test, which takes a sample of the ditch measurements and all the background measurements. And this essentially just looks to see if the two data sets are different, are significantly different. If they are significantly different, then obviously we can detect the ditch in our data set. So basically we can cut off, essentially this all goes down to an R factor, which is basically the same as a correlation coefficient. So a rating of 0 means there's absolutely no ditch there. A rating of 1 means we're seeing the ditch, well, 100%. So I had a threshold of 0.4, and I said if the data shows a mark of less than 0.4, we can't see the ditch in the data, it's just noise. If it's above 0.4, we can detect the ditch. Once we've gone through that stage, we then can see how big the magnitude of that ditch is. And this is essentially taking a line of data from within the ditch and a line of data next to the ditch and working out the percentage difference between the two. Once we have that, we can calculate the contrast factor by times in the detection by the magnitude. And this produces some quite interesting results. If we can see a bar in the bar chart, we can detect the ditch, and the length of the bar tells us the magnitude of the anomaly. So again, at free draining soils, we can see the ditch all the way through the year. We are seeing very different magnitudes of the anomaly though, especially over this very dry period we had between September and November 2011. If you could remember, that was actually a drought. We had a drought in the winter period. Interestingly, at our sites on the clay part of the fields, we're getting our best responses from our ditch during that dry time, 2011, but we're only seeing our ditch in some of the wettest months, 2012, in Diddington, which isn't very helpful. So I wanted about looking at the weather data and how to sort of most accurately quantify how these responses are changing to weather. And as we know that, as Dan mentioned before, temperature also affects the conductivity as well as the rainfall. So I actually put together an evapotranspiration calculation, but it takes a whole lot of the measurements we take from the field sites, the humidity, the wind speed, the temperatures, and I basically take that away from the rainfall, which gives us an estimated cumulative moisture balance from the start of our survey. And as you can see, both sites show similar trends, but are actually quite different. So our site in Cirencester gets very dry. That's our drought period here. But then once we get to about December 2012, it just keeps getting wetter and wetter and wetter and wetter. And actually our last month of survey would be our wettest month. At Diddington, we see a much more increased drop-off. It's a much drier area of the country, as we suspected. And when we start getting the rainfall back again after December, it never actually goes above where we started. So we see a much drier situation at Diddington than we are at Cirencester. So how do the contrast factors of our resistance data relate to those cumulative moisture balances? Well, I first put the Cirencester data, the cherry crops data against the cumulative moisture balance, and got a very disappointing 0.1 negative correlation, which basically means it doesn't correlate whatsoever. However, when graphed, it was noted that these 3 driest months we had might be the thing throwing off the correlation. So excluding those 3 months, we suddenly have a 0.82 very significant correlation to data, which basically I think suggests we're seeing as the soils are getting drier and drier and drier, anomaly is increasing and increasing. But once we get to a certain point, cut-off point, The ditch also starts to lose its moisture, and that's why we then see a drop off in the anomaly. At quarry field, again, we're seeing a negative correlation, so we're actually seeing a better response as the fields get drier. There is no drop-off in the really driest months. In fact, we're seeing our biggest contrasts right at our driest times. And this is especially true for our smallest probe separations, so our shallowest soils, we're seeing the best response. Frustratingly, at Dinnington, we're getting an opposite trend. We're seeing a positive correlation to our data sets. So at Dinnington, as it gets wetter, our contrasts are getting bigger. I haven't quite worked out why this is happening convincingly yet, and I'll have to keep on thinking about that. So that's a brief summary of what I just said, essentially. Again, I'm sure these slides will be available for a minute. So what have we learned just from our Earth resistance data? Well, there's some common misconceptions. In our data set, there's no seasonality whatsoever. I'm not saying there isn't seasonality in data. As I said, this was a very unusual year, but we're not seeing it here. There's no sort of suggestion that wet or damp conditions might give you the best response. As we saw before, different ditches seem to give you different responses over different weather conditions. And therefore, pursuing some sort of overall best survey time is a bit of a fallacy. It's definitely not. It definitely is ditch specific, which might make modelling a wider model quite difficult. So when are moisture contrasts at the most accentuated? Well, I tried to look at what might cause the contrasts, and for this I incorporated my electrical imaging data sets. For those who are new to geophysics, basically this works on essentially the same principle as our twin probe mechanism, apart from we have lots of probes going a long line so we can get a nice section through the soil at various depths. I went away from the traditional sort of environmental time-lapse methodologies used in geophysics and thought of actually incorporating our excavation data. By scaling our excavation plans and putting that onto our data sets, we can start to extract actual data from our contexts. So this is basically 5 of our contexts from Cherry Copse. So I've omitted the topsoil and the natural underneath the ditch. So we're trying to look at what causes our ditch anomaly. Straight away you can see these blue and red lines at the bottom follow extremely the same pattern. These are our subsoil and top of our ditch fill contexts, which are silty clay and sand clay. Now I half wonder if these are actually the same context, and actually we're seeing a difference in excavation because of big bioturbation or ploughing trends, making that a slightly different colour. And I'm actually seeing the best contrast for that ditch in context 9, which is the bottom of the ditch fill, this sort of pinky colour. And you'd expect the best contrast there because the contexts 4 and 5 are basically very free-draining limestone weathered geologies. So I thought I'd look closer into this relationship. And by looking at the difference between the context 4 and 5 and context 9, we end up with this sort of pattern. This sort of pattern correlates quite well with our contrast factor data sets at Cherry Copse, especially at our 0.75 pro spacing, which correlates 0.7 to significant to the 0.01 mark, which is quite nice because our context 9 is between 0.68 and 0.92 metres, so it's bang on that 0.75 mark that we want it to be. We can also then cross-correlate this with weather measurements, which found to be the best sort of cause and effect to be after about a 4-week time lag to moisture conditions at the surface. So our ditch at Cherry Copse is what I would call our textbook ditch. It very much follows the same sort of model that Armin's got in his books about increasing magnitude over drier months, but saturation gives you a smaller anomaly, and if it dries out too much, you'll end up with a smaller anomaly. It's a really nice textbook example of what a ditch should be doing. At Quarryfield, we have a different situation altogether, however. If you remember a few slides back, you might remember that our smallest probe separation at Quarryfield, our shallowest resistance measurements, showed the very greatest contrast to results. And if you also remember, the ditch feature was a positive anomaly, so it's a high resistance anomaly. When I extracted the ERI data sets, all contexts showed extremely similar histograms, which we might expect because it's all clays. Even the ditch fills are essentially the same sort of clays as surrounding it. That's why it's such a hard anomaly to find. However, I did notice that context 1 did have significantly higher readings with it. And when I actually looked at the data, it was actually the data in topsoil above the ditch that was producing these consistently higher readings. So here's the box and whiskers of context 1 around the ditch compared to context 1 just above the ditch. So what we're seeing, I think, here is an impact from what we know, and we haven't spoken about yet, is in the ditch, which is an old drainage ditch, and it's still got the ceramic pipe in it. So I think what's happening is, as we're getting drier and drier soils, the drainage ditch is almost acting like a sump and essentially pulling moisture down from the topsoils, which is creating a high resistive top layer of soil, which is why we're getting anomalies, and especially why we're getting anomalies over the driest periods of our survey season. So what can we take away from all this? Well, I think the main thing to take away is each survey area is extremely different. The analysis of data, which I haven't gone into yet here because I'll run out of time, is different again. Each field reacts differently to the weather, and there seems to be different reasons each time. Cherry copse is our only textbook model. So I think I'm maybe bringing up more questions than answers with my research. I'm struggling to work out how we can even make a wider model if we wanted to. Yeah, so future work for me is finish my PhD essentially, and potentially try and look into modelling afterwards. I know Dave Jordan's probably going to do something on this later on, so we started looking into the possibilities. But I imagine there's tons of scope for future research on various soils, various ditches, various features, to try and understand this problem a little bit further. Thank you very much for listening.
That seems to illustrate the local nature of variation, and probably has a lot full of community actually within these data sets. Dave, where's Dave? Dave's going to give us the final student presentation. You got quite past yesterday. They've taken up all the slack.
Okay, so I'm David Stock, a PhD student here at Leeds. Can everyone hear me okay? Okay, and basically my PhD is on the sort of airborne part of the DART project. And I'm basically looking at the formation of vegetation marks on arable land. And we're doing this using LiDAR data, spectroscopy, both imaging, airborne spectroscopy and ground-based spectroscopy, and aerial photography. So the aims and objectives of this work is to kind of look at contrasts and how they change over time with weather and particularly land use. There's been a slight shift in my work because really we don't have close enough observations to look at the state of the crop as it changes over time. So I've been much more concentrating on how to actually detect subtle contrast with different sensors that we're using. Namely what we can detect with sensors and how we deploy them optimally in different contexts. Adam's kind of covered this, because I'm conscious I'm running out of time. And there are some yeah, challenges with the data specifically. There's a very high dimensionality, so the hyperspectral can have hundreds of different bands. There's full waveform LiDAR, which is a kind of, again, a hugely kind of rich data set that we can look at. And it means there's lots of redundancy and lots of sort of repetition where we find things. One of the issues is there's no unique spectral signature for archaeological features. This is a quick example of something we've seen before. You see this beautiful sort of radial street pattern from some amazing city, but actually it's lynchets caused by the pigs walking up and down the electric fences. So if you employ sort of standard remote sensing, brute force computation, classification techniques, you're going to pick up a lot of this stuff and not so much of the archaeology. But that's just something to bear in mind. Said that. So the ground-based methodology, basically we're doing spectroradiometry with an ASD field spect probe, which gives a spectral profile over the 350 to 2,500 nanometer range, so just the other side of the visible to shortwave infrared. It's a 3 nanometer-ish sample range, because they're not necessarily truthful in terms of the manufacturer specifications. This is the instrument, big heavy thing, old laptop. And in conjunction with that, we've been taking sectometer readings, which kind of quantify the leaf area index of the crop, surface coverage using your vertical photographs, and looking at tillering in the early growth stage of the crop development. So how many little shoots it throws out. I didn't have blind somebody accidentally. Yeah, this is sort of typical field survey. I think this is from April last year. We're in Quarry Field in Palm Hill. Everything's covered in mud. I've also got airborne data, so we've got Eagle and Hawk from NERC RSF. We have full waveform LiDAR, orthophotography from the survey camera, and we've got similar data sets from the geomatics group as well. We have CASI hyperspectral, discrete LiDAR, and orthophotography from them. And I'm analysing all this using Python software that I'm writing myself. And basically that's to do spectral analysis, namely continuum removal, vegetation indices, and red edge position. And it also sort of looks at the LiDAR data. So I'm just going to give you a quick example. This is a bit of us hurrying up to get onto. It's more fun. Basically, a quick example from Dinnington in 2011, over the course of 3 weeks. So basically from the 14th of June until 15th of July. And basically you can see these beautiful crop marks here on the ground. These lovely features. You're seeing a kind of variation in greenness. You can see an obvious increase in biomass and the overall height and health of the crop. 2 weeks later, June the 29th, you can see you still have this height variation and a kind of increased development in terms of ripening of the crop over the ditches compared to the areas outside the ditches. And basically this is after the crop is senesced and ripened, just before harvest, and you can see the biomass variation, but there's very little variation in terms of colour. So bearing that in mind and looking at that, I've been looking at spectral differences from spectroradiometry using continuum removal from different absorption features. So basically, considering the 670 nanometer absorption feature here, which is the absorption of chlorophyll, where your classic kind of multispectral NDVI is based, where you look at the minima and maxima of absorption and reflectance, respectively. And what we're trying to do is normalize out the effects of the biomass and illumination geometry from that, so we can see what affects what. This is half a t-test. So basically the black areas here are, I've got the dates wrong on the graph, never mind, on the 14th of June. So the absorption index is just a ratio between the absorption minima and maxima, and you can see that showing the strongest contrast. The band normalized is essentially using continuum removal to look at the variations in pigmentation. accounting for the variations in biomass. And you can see there's very little variation there, and the absorption maxima is just the depth of the absorption feature from the continuum line. So you can see that basically we have change over time, but the biomass sort of remains constant. So essentially, looking at that, I then wondered if we could use a LiDAR to detect biomass variations. Conscious I'm running out of time, we looked at the full waveform. This is an example waveform from one of our sites. Quite often when you're looking at sort of full waveform LiDAR for forestry or taller crops, you'll actually see a double peak and a lot of variation in the width of this peak. But given we're dealing with a very low and sort of scrappy agricultural crop, we don't really see that much variation in terms of the width of the feature. We see variation in terms of the overall sum of intensity, which is essentially what this is doing, but I'm just essentially going to gloss over this. And we see a good correlation between the sum of intensity and the archaeological features, but the best we get is from the vegetation height. And essentially we're deriving this by looking at discrete return LiDAR data. So this is a quarry field at Harn Hill on the 23rd of March, where there's bare soil. We have one LiDAR survey there, and what we do is we subtract that from the survey on the 20th of June, where we have a mature wheat crop. And there again is a survey, and you can see sort of little bits of variation in the crop canopy. That's our scaffolding tower and fan from the thermal experiment. And basically we subtract the bare soil from the maximum crop height, and we essentially get a pretty good model of the sort of mass of vegetation. And you can see all the rig and furrows showing up beautifully. There's the ditch and quarry field. There's some sort of enclosure system up here, but it's sort of outside this stretch. So this works really well, and it's quite exciting because using LiDAR to look at crop marks isn't something that's generally being explored. So just to give us another example, basically this is Diddington again. Basically we have our two sites we want to consider. This is our TDR box for the pasture field here. This is where I've been doing my spectroradiometry transects. A1 running up here. And basically this area here is the interface between the clay soils and the sand and gravel terraces. And I just want to kind of compare the returns from both areas. So looking at the sort of west side of the A1 on the clay soil first, here's the ortho photograph from the 27th of June 2011. And you can see we've got kind of little bits of enclosures. We've got a round feature here, which is probably a lovely roundhouse, and these sort of pitty things, which I would interpret as rubidizer. Looking at the vegetation height model, we don't get anything like as good information from that as we do from the aerial photograph. You can kind of see there's things going on, but mostly because you know they're already there in the vertical photograph. But when we look at the absorption ratio from the Cassie hyperspectral, that's actually really washed out on that screen, isn't it? That looks beautiful on here.
It's a bit better on these monitors, David. Okay, on the monitors up here.
Okay. Basically, we can see a lot more detail in this. Things like this double ditch, kind of segments of ditch up here that. Oh no, I'm jumping ahead. Wrong direction. Are a little bit more subtly expressed in the aerial photograph. Now, the important thing, I think, from this thing is that no single one of these sensors is giving you best results. But the other thing is, the Cassie hyperspectral data is 1 meter spatial resolution. So the spatial resolution is not be all and end all, but it's considered to be largely by the archaeological community when you compare it to the 8 centimeter resolution. So moving across the road onto the free draining soil, you can see we've got all these beautiful, lovely, complicated, sort of Romano-British settlement crop marks, paleo channels, geological crop marks, post-medieval stuff. And it's lovely. We get really, really good definition on this photograph because, as you can see from the shadows it's taken in the morning, which is when you really shouldn't do your airborne surveys from the point of view of the high spectral, but the geomatics group have done that kindly for us. And the vegetation model basically shows a lot of the same features. Not quite as much detail because I think you don't have that sort of shadow relief. But then interestingly, the absorption ratio shows much less. And bearing in mind these are all data acquired on the same day. They're about 700 metres apart. It's the same crop, it's the same wheat, all part of the same crop rotation, sown at the same time. Basically, finding the optimal sensor is not just as easy as saying, just use this. So basically this is proving kind of interesting. And I think it's down to the variability of the archaeology, the variability of the context it's in, and the fact they're looking for very small things and very big data, and I haven't even got onto the weather yet. In terms of further work, I'd like to look at the scan angle from the LiDAR because we have that encoded, so we can actually look at the sort of bidirectional reflectance factor and how that affects the return of that vegetation height model. I need to do more sort of spatial analysis in terms of filtering my inputs and also degrading the bare soil model because I think it may be possible to use lower resolution data and keep repeating that. And then do a statistical comparison of the different sensors or the features we've identified from geophysics. I'd like to thank NERC ARSF because this is a slide from when I did the presentation for them, so they're first. The Royal Agricultural College in Thornhill Estates for letting me traipse all of their land and molest their crops, and all of you. Thank you.
What we've heard in the last three presentations is the basic data sets that the projects work from. Obviously very disparate and all highly complex in their own way. Fortunately, we've got Ant here to explain how they all fit together. I hope. All right, so it's over to Ant.
Oh, excellent. I'll be able to see what I'm doing. Please do bear with me. Let's make it amusing. I'm going to end up killing my own neck. Right. Okay, thank you, Chris. Bringing it all together. Yeah, thank you, Rob, David, and Dan. This is really about trying to bring together all those different data sets and associated weather data, which I didn't actually say anything about in the introduction. So, broadly, archaeology as a discipline includes a great reliance on relationships between data, interpretation, practice, and theory. We collect lots of evidence or excavations, that's mainly most of us like to call them, and we get more evidence by doing more excavations or more analysis of stuff. And then we start to connect the dots between these things, normally through a process of some kind of theoretical model. And we can produce a whole range of different theoretical models that can join the dots between these different bits of evidence that we collect. And as we gather more and more evidence, we can start to cross off some of these theories that we generate that just don't fit the data anymore. All the theories that we generate have assumptions built into them. We try to focus on the ones which use the fewest number of assumptions until we quite a kind of grounded model which we're pretty confident in as a reflection of the past. Although that model is always a model of the past and it's never really something that's rich enough to represent reality, if reality ever actually exists. Because we have the theories, it says we have different contextual viewpoints in which we can look at the past. And so many of these different models may be equally valid. So great, we have this wonderful build-up of data which we can theorize about, we can produce models about, and we can produce stuff about. Now, if we're starting to extend that and produce bigger models to look at national or international frameworks, we actually want to introduce all of those data together. The problem is, how do we start to pull that corpus together? We have the accessible knowledge, the stuff we're aware of, and we can actually get access to. There's the inaccessible knowledge, well, the stuff we're aware of, but it's behind some form of barrier. It might be in a repository which we don't have access to, it might be behind a paywall, some form of system that means that we just can't get it. Then there's a whole heap of other stuff that goes on that we're not aware of that might actually, have some part to play in the solution to a problem we're forming. So we have this potential knowledge cloud. Some of it's accessible, some of it's not. Now in Dart, we have a whole range of different data. And we need to make sure that it has an impact in this landscape. So it doesn't just go in there and just trickle away. We want it to actually change the way that it makes people both think and conduct what they do. And one of the ways we decided to do that was to adopt an open science philosophy. So wherever practical, all the data will be in the public domain as soon as possible in accessible repositories. I remember writing that. It's actually proven quite difficult to do in practice. I can wax lyrical to you, probably over a beer at the end of this event, why it was so difficult. But we've achieved quite a good thing, which I'll now talk about in a bit more detail. The thinking behind this was that by opening up and dynamically sharing this data with a broad consortium, we can improve scientific process, improve results, improve impact, and have a bit more wow. We can build communities of practice, different end users. And our next presentation from David is demonstrating exactly that. So this requires a corpus of open and accessible resources using open methods, open processes, open licenses, open science, bringing in more communities, having science within society. So as part of that, we have our data repository. This is based upon CCAM, the Open Knowledge Foundation. It's called a metadata system. We have explicit licenses, liberal licenses using Creative Commons by attribution and ODDL, so open database licenses, to encourage reuse. The reason why we've got by attribution is so that we can facilitate tracking. We know who's using our data, but we don't know because it's not enforced. We'd like to know, but ultimately, I want everybody to use our data and reuse our data. It has the Open Access Initiative, the protocol for metadata harvesting. I mashed that up a little bit, but basically, we can share our metadata and it can be harvested by other institutions. The ADS, Europeana, can basically get hold of our metadata. The data has a URI, so it can be called in by web processors, which we'll talk about in a little while, and CCAN itself has its own API, so it can be part of a programmable network of stuff. So here is the Dart portal. Within the Dart portal, this is live, by the way, so expect it to break. We have data. We have our hyperspectral, the LiDAR, vertical array photographs, bulk electrical conductivity from Dan's data. I have a look at thermal stuff. So you get a summary of what's going on in each of those data collections, as it were. And within those collections, we have a little bit more information about what's going on there, why the data's been collected. These are all our different data resource objects. We have metadata about the collection itself. Note we have you can cite that collection. All very useful. And a whole range of different metadata tags. Most of it is based upon the ADS metadata system. We've extended that with other metadata frameworks. We have an ingest framework equally that makes that whole thing very easy to do. And so when the ADS are archiving our data, which we are doing at the moment with geophysics, they should be able to pull everything out dynamically from what we have here. That's the aim. We'll wait and see what it is in practice. Now, we can go down to an object. Let's do this one. There we are. So that's me in near infrared, taken by John. We have a little map where it is. We have specific metadata now about that resource object, and you can reference it individually. So we've got lots and lots of metadata. And we've got lots and lots of resource objects. We have explicit licenses this stuff can all be reused. Great. So you can access our raw data. You can recreate your own models based on what we've done. We've also created an integrated spatial temporal database. This has been modeled in UML, so you can see the entity relationship models between all of our tables and our lookup tables. We've got the definitions of constraints and relationships all in there. We're also able to convert that UML into PostgreSQL specific SQL scripts. So those who use Postgres basically take all that data and load it up as one. This creates one big CSV file which can be ingested in this 2 GB thing. And this is the environment we're likely to use for both online data mining and some of the collaborative analysis, which I'll go into a little bit more detail now. Most of the stuff that I'm writing is done in Python. Again, these are all shared under liberal licenses to encourage reuse. It's based on accessible URIs and potentially accessible databases, and still need to resolve what we're going to do with that database in respect of making it open, i.e. hosting it in an open way. So basically you can take the code that I generate and run it in your own environment. There is no firewall or no barrier that blocks you from analysing the data in the same way that I do, which I will show you. Now, this is my IPython notebook. Is this what I want? Yes, it is. So, in here, this is how we can process our data. The top is telling us the libraries we want to use. And I'll just run that script. And now it's going to open up one of our data sets, which is on the server. Okay, and here's a citation for it. So, if we run it, it's all working. A live demonstration, it actually works. And here's a quick summary list of the data that's just been imported. The next data set here is starting to, the next process here is starting to grid that data. So we've now gridded the raw data into a 20 by 20 array. And we can plot that data. So what you have here is an audit trail, a full process of what we're doing from our raw data to how we kick it out at the back end. So you can see how we've taken our number, or taken that raw data as a numeric array, and start to process and transform it. It is completely transparent what we have done in that thing, and we can share that with everybody. So if you want to see how we generated pretty pictures, you can see how we generated pretty pictures. If you want to get an understanding of the assumptions we've made when we've processed from raw to interpreted output, you can see what we've done. If you disagree with it, you can do it yourself in a different way. And you can build on these techniques. Come on. That's fine. Okay, right then. So here's the same thing now, but this is based upon the Postgres environment. So we have a few slightly different libraries. We've got a different connection script here. Okay, we can still bring in the data. We can still re-array it. But what I've done, okay, so we're plotting it out here. What I've done now is just create a number of little filters over that data. And we can plot those out and create something that brings them all together. Wonderful. Easy life. But we can also very rapidly reapply that to other elements of our data. So I know here that I want to look at sensor configuration C, for example. And we can rerun the whole process. You see we now don't see the ditch feature come through in our raw data. You can possibly see something here, it's probably better on the monitors up there. But if we run through on our different filters, you can see that we're getting something very clear when we're using, I can't remember what filter that is down there, with the data. But again, this is a process we can share, it's transparent, it's open. It's very easy for people who are reinterpreting or reanalyzing this data to see what we've done and to look at the whole process that we've used. Fantastic. Right. Okay, so the whole point of that is to start to improve engagement, data, collaborations, science, impact, and potentially serendipity. Yeah, how we can just get people to look at data and do interesting things because they can. So we're opening up our data. One is a reduction in the data mountain. There's value-added resources that actually can be reused. There's huge engagement potential and it's produced social good. It's access to traditionally inaccessible data. Hyperspectral data is kind of quite difficult to get hold of, or is rarely got hold of the archaeological community. If we're also opening up our processes, we should be able to get more eyeballs looking at our code, making sure that the processes are actually robust as well as transparent. So we should be able to generate better models. And we can start to deal with some of these trust, provenance, and credibility issues, which are problems within the open data community. And it's not just kind of the science element, but it's also what's going on with government and their open data issues. We then have open practice, as I say, more people looking at the data, looking at the processing itself and trying to improve that. So increased understanding, increased transparency and reuse. We're not generating black boxes. We're not just clicking the button and getting something coming out the other end. You're understanding that transformation process. Collaborations. We can start to converse and engage more effectively with that whole cluster of different organisations affiliated with what we do. Toby Mottram from Royal Agricultural University is speaking this afternoon. We are now, discussing this afternoon. But we can start to look at how there is synergy between the goals that we want to do as heritage professionals and what the farmers at Royal Agricultural University and researchers at the RAU are doing as part of their day-to-day activities. Some areas there is significant overlap, and we are always the core partner. We need to work with these communities if we're going to have a much larger impact and to deal with stewardship, not just on a local level. We're talking about ramping this up at both an international scale as well. Improving impact. More reliable models should lead to better decision-making processes, better understanding. We should have easier reuse and engagement facilities because we're providing this in well-understood and open formats. And this whole serendipity thing, which I do really buy into, we've got this free flow of ideas, this free flow of data that allows people to model in very effective ways and model without having to spend their time writing grant applications to get to small bits of data. It's there and it's reusable. And it's open citizen science, producing something where you can have variations in different communities of practice, different community groups that can come together to solve problems which they address. It doesn't have to be a major research problem, it doesn't have to be major impact. It's something that a small or large scale community can just resolve on their own. So, why do this? The EU says so. Open instructions for open science. Good science diversity matters. Enabling this is not just good for science, it's also necessary for smarter decision making. So, it's ticking boxes for the EU. The UK government says so. Data to optimise its value to society must be open, shareable, and where practical, it should be free. And this is a document that came out only a few months ago. Royal Society says so. Science is an open enterprise. Recent decades have seen an increased demand from citizens, civic groups, and non-governmental organisations for greater scrutiny of the evidence that underpins scientific conclusions. So we're looking at evidence-based research. We're looking about the impact of evidence-based science in policy, in curation, in a whole range of different activities which we undertake on a daily basis. EPSRC says so. EPRC-funded research data is a public good, produced in public interest. It should therefore be made freely and openly available. So, that's dark data. It's openly accessible. Please use it. Thank you.
So, Sian has described the availability of the data sets that the project have produced, and I think Dave's going to talk a little bit about how one may actually use these sorts of data sets as can I say, an outsider?
Yeah, absolutely. I'm an outcome. Sorry? I'm impact. That's right. Okay, so I'm David Jordan. I work at the Geoscience Institute at the University of Mainz in Germany, and I'm a soil geoarchaeologist. So I spent most of my life using soil methods to look at the structures of the stratigraphy of archaeological sites. Let me bring this bit to an end. Get mine. I just added a slide to my show, if it recognises it. No, it doesn't. Oh, well, never mind. I'll use the original one and talk about what I was going to show. Okay. So, in Mainz, we are working on the detailed analysis of the structure of archaeological deposits to try and understand their detectable behaviours. In other words, we're using geoarchaeological approaches, micromorphology, the analysis of the electrical conductivity, dielectric properties and so on, within the soil at a small scale, using samples taken from excavations and from field survey data to understand the properties that we then go on to detect. And central to this is being able to describe some of these properties in a more rigorous way, where we can numerically, using models. And that's what I want to talk about today. What I've been involved in the DART project is really very much an extension of the work that you've seen being done by the students and what's being presented for them. And I have to say first that I'm very grateful to DART for giving me this opportunity. So here we have a typical archaeological representation of a set of typical archaeological features, prehistoric ditch, and the drawings we make of them. These are our starting models in many circumstances, representing this extremely complicated physical reality in a relatively simple way. We know from many years of field experimentation and in archaeology and before that in geology and in engineering that we can create, and here is a very simple modelling tool, a representation of distributions of, for example, electrical resistivity in the ground, looking vertically down through the ground, and generate from that our expectation of the detected distribution of resistivities at the ground surface, and then compare them with what we actually see when we do a survey. And this kind of modelling process is extremely common in engineering and geology, as many of you will know. The models that we generate, the models that we can use can also be based on our understanding of the fundamental physics of the soil. So here we have two equations, the Rhodes equation and the Waxman-Schmitz equation, developed both of them very many years ago. The Waxman-Schmitz equation based on the RG equation, which was first published in the 1940s, based on much earlier work, describing electrical conductivity, electrical resistivity, or 1 over resistivity in each case, within soil and shaly rocks in terms of more fundamental properties. The Rhodes equation describes conductivity in terms of two pathways through the soil, a wet soil pathway and a direct pathway through the soil conducting through macro pores. And here we have something similar for the shaly rock conductivity, where we have a formation factor, which is geometric factor, and the resistivity of the water within the rock, and a term describing conductivity through the clay within the shales. Essentially, the important point is that we can predict from certain known properties the kind of electrical conductivities that we would expect in specific circumstances. Having done that, we can build crude models of archaeological structures. Here's a very crude ditch, consisting of a series of layers, a cultivated horizon at the surface, and stratigraphy beneath, and from that predict what we would expect to see using electrical resistance tomography of the kind that we saw earlier from rock at the ground surface. And by using models of this kind, we have the liberty to change conditions without having to go into a field and pour water on it. We can create mathematical representations of reality which we can then adjust. Now, this raises all kinds of difficulties. Realistic models of the behaviour of soils are extremely difficult to make. They're very difficult to do because soils are extremely complex, diverse, and exist within diverse environments, rainfall and so on. Archaeological remains are vastly more complex, because they are not only complex in themselves and very diverse, they interact in complex ways with their environment. And soil, hydrology, structure of archaeological remains are very variable at many scales, so why bother? Firstly, we have real problems, as the DART project itself has been based on this question of targeting our methods, the right methods, in the right places, at the right time of year. So our motivation for understanding the mechanisms, as been explained to us already, is very strong. Secondly, we do modelling anyway. When we decide, for example, as commercial operators going out and doing surveys, what methods to apply where and at what time of year, we are making assumptions which we cannot usually challenge because they are not terribly explicit. We say more or less it's like this at this time of year, at that time of year, and that's wonderful, but our models are very difficult to challenge while they remain relatively relatively fluid in the way that they're stated. So getting better, I'll come back to that point. So, what I was doing several years ago was creating models of typical ditch structures like this, adjusting the water contents at different times of year, and using equations like the Rhodes and Waxman-Schmitz equations to calculate the contrast that we would see in resistivity using typical electrical resistance arrays. And here is the difference between a contrast in summer and a contrast in winter, similar to the kind of pictures that you've been seeing already from what the students were doing. Here is the excavation of the ditch at Diddington, and I wanted to show you this because you can see we're down to a level of saturation at the top of the gravel at the bottom there. And from this, we generated a description of the hydrology of this material. Why the hydrology? Why is this important? Well, again, we've already heard that the water content in the soil controls a great deal of the geophysical properties that we then go on to detect from the ground surface. And here I'm using a modelling system called Hydrus, very widely used. And here is approximation to our Diddington ditch, not in the clay field but in the gravel field, with the various elements to it, taken directly from the recording. And on the right-hand side, in the field, and on the right-hand side you can see two different stages within the model using the rainfall data that I got from Cambridge Botanic Gardens, the nearest place that I could get reliable rainfall data daily, because we didn't have it from the site itself, showing changes in water content derived from the hydrological model 14 days, 2 weeks before the final period of fieldwork and on the day of the final period of fieldwork itself. These compare reasonably well, the second one with the measurements of water content we've derived from our own measurements in the laboratory. So we know that the model is not far off the truth. What we then did was output this distribution of water content and other properties and use it using one of these equations to calculate the expected distribution of values of electrical resistivity within the different strata. And the idea is that we compare this with reality to see how well the two compare with each other. So this is an inversion of one of the data sets from Rob's work. Thank you very much indeed, Rob, for this information. And here is our distribution of the resistivity values that we have calculated from the hydrological model and the geophysical model together. There are all kinds of things wrong with it. We don't model the boundaries between the different volumes of material at all well. Our understanding of the behaviour of the gravel underneath, which is saturated but resistive, is poor. And the reason for this is the models are not entirely appropriate. The Rhodes equation, which we have used to create this distribution, models the behaviour of gravels very badly indeed. And so we need a different approach to it. And that's something that we're looking at investigating at the moment. I'm going to run out of time. But nonetheless, these provide us with tools to extend the data gathering that the students at our projects have been undertaking and explore the way we the sort of physical properties come about in a more flexible way. And what we are doing at the moment is carrying out laboratory analyses of the electrical conductivity against water, water against electric permittivity, and other properties to try and improve these models and tie them down to the distribution of physical reality in the ground. That's work very much in progress, and so I can't report on the details of that yet, but that is really something where we look forward to working with the students in developing this further. Now, one of the big problems that we're having is the way that we translate the reality of structures in the ground into the archaeological record. Because we do this by dividing up areas of our soil into strata. However, our boundaries really aren't like this. The reality of the distribution of materials in the ground is very, very continuous. And if we look within pretty much any one of these, we will see that there are big variations within each of these in terms of texture and structure and so on. One of the advantages of working on this particular ditch is that it's relatively coarse material and it's therefore relatively weakly structured, and we don't have to worry about macro porosity and its effects on the water movements and on the distribution of geophysical properties too much. That wouldn't be the case in the clay field, for example. But the difficulty we have is that the translation from physical reality into archaeological record gets rid of so much information that it's very hard to make physically useful models, numerical representations as a result, because the boundaries misrepresent the distribution of physical properties. In a necessary way, this is the way that we've always done archaeological recording. It's necessary simplification. The problem, therefore, is that working back from archived information, even where we have good archived records of soil, strata, physical properties, to geophysical properties, going back to the records that we already have to understand previous geophysical surveys is very difficult because of the amount of information lost in this process, and this is something that we should perhaps be discussing. Okay, I'm going to, given the time, I'm going to skip through these, which are examples of previous work. The other thing I just wanted to mention briefly is that it's all very well making a model from a set of records from a particular excavation, but we know that if we displace ourselves a little bit in one direction or the other from the line of, for example, an ERT traverse, we are very often in material of very different kinds because of the variability of the fills of a ditch feature of this kind. Here we have a relatively uniform set of parent materials. So we have these gravels underneath and over the top layers of relatively fine material which have horizonated over time to form relatively consistent materials over areas of 10 metres or so. If we instead were in an area that's been heavily mixed by periglacial cryoturbation, we would find that we had enormous variation over very short distances, and anything we tried to do locally would be invalid only a couple of metres away, and therefore we need three-dimensional understanding if we're going to make anything of it, which makes the purpose of modelling even less clear. In other words, this kind of use of modelling in understanding structures is valuable only in certain circumstances. The question is, can we identify what those circumstances are? The answer probably is yes. So that's probably left you with a lot more questions than answers, which is the purpose of today. But let me move on. Yes. I just wanted to finally show this picture. This is taken from Ken Klein's wonderful publication on work at an army camp, abandoned army camp in the United States. Here we have combinations of images taken from different geophysical and remote sensing data, picking out different structures to different degrees of clarity. This has been done either by the simple combination of colour bands attributed to resistance data, IP data, EM data, whatever, or, in the very final one of these, a statistical analysis based on principal components analysis. The point about this is the principal components here probably have visible meaning. There's probably something behind this to do with water content, for example. But because it's based, all these are based on simply combining the imagery in some way without referring to the processes in the soil that generate the different responses that have produced the geophysical images, they don't have much predictive power, explanatory power. If, however, we take our thermal data, our crop thermal data, our ground thermal data, our resistance data, our radar data, and bring them together using descriptions of the physical basis, physical properties of the soil. We have perhaps the opportunity to extract physical information from these various models. So that's the challenge for the future, and that's where I hope we'll be able to go further. The important thing is that given the complexities and difficulties of making realistic use of these immense simplifications, which what numerical models of soils and archaeological structures are, making use of them, we have to be able to understand how well they represent the real physical behaviours of soils. And to do that, we have to do geoarchaeological analyses. We must be looking at the fine structure of the soils to see whether the pathways of conductance, for example, in those soils, which are represented by the equations, really do represent what's going on within particular soils, within the structure themselves. So, thank you very much.
Thanks, Dave. It's great to hear that the community is already working on the data that we've collected, and I think there's there's going to be a lot more research in that area in the future. Tony's going to tell us a little bit more about how you may get your hands on that data, perhaps, or is that what you can do? Data mining, possibly?
I'm going to very briefly mention how to
Okay.
get your hands on it, and can probably fit in more on that. Here. Okay, so my brief was to talk a little bit more generally about what we might do with all this data. I should emphasize at the start, as I'm not an archaeologist. My background is in artificial intelligence, in knowledge representation, in machine learning. I've done a lot of work with large data sets, particularly video data sets, to kind of have, I think, some interesting analogies for the kind of data we've got here, and as much as they are spatial temporal, there's a lot on it, there's often a lot of uncertainty and variation, noise, coincidences in the data. So this is, again, too small to see, but again, this is available on the ART website. This is Ant's description as a UML diagram of the data. What all the different fields are, what the different fields with all the different records are, what the different fields in those records are. Rather than go through the detail, I just thought I'd summarise it with just saying exactly what kind of data is really in there. So it's a relational database. We've got records describing the fields in the agricultural sense here, not the field science sense. And that's kind of static information, saying where they are, what the geology is, what the land use is. Well, land use might change, but it didn't change within the time of our measurements. The trenches, those were dug once. They've got a start and end points. And then we've got measurements, which are mostly dynamic information, which is they will have a when, a where, and a particular set of values. And that varies from all the different kinds of things we've been hearing about today, the hyperspectral, the various different kinds of geophysical measurements, weather data, soil samples were dug up and analysed in the labs at Winchester and Birmingham. And the data generally has spatial aspects when it's dynamic, it has temporal aspects. The temporal is different time levels of granularity, time of day, season, which may not be relevant, as we've heard from Rob. The time within the year, the field location, the transect. We got depth information in some cases, not just X, Y, and we've got lots of different spatial granularities. Obviously, different sensors are measuring the data at different levels of representation, spatial granularity. And we have some of the sensors that are giving us measurements basically minute by minute, hour by hour, weather and the probes from Birmingham, whilst other ones we have flights which we've flown about 4 or 5 flights, and those are clearly much more occasional and a very coarse granularity. So we've got a lot of data, but it's very heterogeneous. It's describing different kinds of things, and it's in very different spatial and temporal granularity. So that's both interesting but also a challenge at the same time. So my brief was to talk a little bit about data mining. I'm sure many of you know something about that, but I just want to summarize very briefly. I have a slide here just about machine learning. I'm just about to start teaching my annual course on machine learning to the students, so there's a lot more than I can say in one slide. The key distinction is between what we call supervised learning and unsupervised learning. So in supervised learning, we have a particular set of concepts which we're interested in trying to be able to recognize it in future data, and we try to do that by then hand labeling particular examples of that concept occurring in data which you already have, and that might be a particular spatial pattern, or it might be some sort of temporal feature, or some event, and we label positive examples of it, typically negative examples too, so things which is an example of an archaeological contrast, a negative example, and then the learning algorithm would then try to find which features are most relevant to that concept, and then build a model which we can then try to use to apply. And there's a lot of different algorithms which can be used to do that. But typically what affects, as I'm saying at the moment, the success of that much more than a particular algorithm is actually the choice of representation language. In unsupervised learning, we're generally trying to find interesting patterns in the data. And this is the key issue, is what do we find as interesting? Because it's interesting to one person, might mean something very different to something else. It might be interesting that a particular feature stays constant the whole of the time, if I'm trying to predict stability in the economy or something like that. Or I might be interested in high variation. So what your definition of interesting is going to very much affect your unsupervised learning algorithm. Often it's a very commonly form of unsupervised learning is clustering algorithms, which try to cluster the data into a set of similar data points. And here, the key issues are what kind of distance metric. If we're trying to cluster and say they're similar, what do we mean by similar? So one question is, what do we mean by interesting? What do we mean by similar? And again, that we can take, are we going to ignore space? Are we going to ignore time? Are we going to ignore depth? Are we going to ignore all the other kinds of features which we have? Or we can abstract to a coarser level, and then features which look initially dissimilar may become more similar. And also there's a question of how many clusters we might be interested in having. And as I say, typically we will do a lot of pre-processing of the data to aggregate the data. We've already heard in some of the previous talks some of the kind of Anne's demonstration a few minutes ago about the kinds of aggregation and interpolation that can be done. So as I said, representation is a way much more important to machine learning than the actual algorithms. Often you find that you try a bunch of different algorithms, they all give broadly similar results. What often affects the results much more is actually how you choose to represent your data. You've got the raw data, but typically you'll do a lot of processing on that before you actually give it to a machine learning algorithm. And that's, if you like, the skill of the model, the skill of the person who's doing it. And it's kind of often something of a black art in order to really go and get a successful model out the other end in terms of a learned model which can then do prediction for you in the future. And there's this big tension between expressiveness. The kind of more expressive you have, either more features, the more different values the features can take, the more relationships you have between things. It means you have more possible nuances which you can express, the more possible models that, the concepts you might want to learn, but equally well, it makes it much harder to find them. Typically, you'll have much more data in order to be able to reliably learn them, and there's always a worry of that you might actually overfit to a small amount of data. So there's a kind of tension. So often it's kind of safer to use a less expressive language, which will then need less data, and it's faster to find it, but then equally well, you may be missing the kind of true concept. There's work done on, often we might hand abstract data. We've got this continuous data. We've heard just in the previous talk about how we might try to take that continuous field and abstract it into discrete areas. And there's work done, particularly in the revision community, about trying to learn that discretization. And you can do it. You can do lots of different kinds of discretizations, and then use a Bayesian information criterion to select which one actually seems to give you the best results against a ground truth test set. So as I said, there are many different algorithms, and indeed there are hundreds more produced every year. And often we combine models, different learning algorithms, so-called ensemble techniques, which gives us a lot more robustness and variations in the data. Some techniques may be better at certain kinds of examples, other ones may be, other techniques might be better at learning other examples of the class of a particular concept. And by having these ensemble techniques, we can get more robustness. There's a lot of open source algorithms out there, for example, the Wecker set of algorithms, but often people end up writing their own. That's something we might have, I guess we've just started to do, but time is nearly at the end of the DART project. As I say, often representation is more important than an algorithm. Some algorithms can make explicit use of sort of background knowledge we've heard already talked about processes in terms of land formation, in terms of erosion, in terms of weather processes, and some algorithms would actually explicitly incorporate that kind of background knowledge into the model building process. So as I say, my expertise is particularly in terms of spatial temporal data mining, particularly from video, where we extract we've got a raw data field now, which is in terms of pictures taken over a subsequence of time, and we extract objects, features from that. And we then have those properties, relationships between objects and features which change over time, and then we try to find a model which will explain that data in terms of events, in terms of event classes, instances of those event classes, which then explain what's happening. So we want to come up with a high level description of what's going on in a particular video based on the original pixels, but at a much higher level than that, and which is going to enable us to predict and explain future video as well. And we'll try to explain as much as possible whilst recognizing there may be noise, there may be coincidences. So just to make that more explicit, we might be looking at a video of an aircraft turnarounds at an airport, which is one domain we're looking at, and we're able to automatically, in an unsupervised way, learn the typical kind of events that actually would happen. We call them event 1, event 2, event 3 in the unsupervised algorithm. But if you look at the examples of event 1, you can see there are unloading events, you look at examples of event 2, there are refueling events, and so forth. But there's that sort of an event-based learning algorithms. There's all the ones which might be looking at sort of particular spatial features of video data. So really kind of brings me to the wrap-up. The question is really, we've got all this data, and I think this can lead to discussion now, is what would we actually try to, what kind of models would we like to learn? What kind of concepts? Rob brought up this nice quote, when moisture contrasts are most accentuated. That's a concept, but can we try to find a way of automating having some sort of operational definition of that, which might not be a simple operational definition. It may be very complex with lots of conditions depending on soil type, on weather, on and so forth. Spatial patterns, correlations between different kinds of processes and features. Ultimately, it really depends as to what's interesting. What is the community interested in trying to extract from this? And that may be very different depending as to what your perspective is on the archaeological problem. So the future of the data is there. It's online. It's free to access. That was a big part of the DART project. We can tell you, if you're interested in accessing it, we can tell you a lot more in detail about how to actually do it, how to get access to it, how to download it. Please make use of it. And that's it. I think it's pretty well spot on time.
Thanks, everybody. There's a couple of things that I have neglected to mention. One, I want to thank Dave Harrison for all his work in building the repository for us. That was great work. But also in response to David Jordan's presentation. One of the things that hasn't really been highlighted this morning has been the analysis of the soil samples, and which feeds directly through to the kind of modelling that David's talking about. So, you know, they are the unspoken partner in this morning's presentation, but we have done, you know, that laboratory analysis is going to underpin these downstream modelling. So don't forget about it when we're talking about things this afternoon.
Okay, actually, what I'm going to suggest is we have a 5-minute break, because I think just give me go to the loo or perhaps get a drink. Okay, so if we can just have 5 minutes off.
Toilets. Gents are down the corridor and on the right hand side. Unfortunately, I have absolutely no idea. Further down, ladies.
Sorry?
This is what I meant.
Yeah.
Keep seeking.
He does. Because I think I'm really
come down with something. Well, nothing, that's the problem. That's, you know, no, obviously I'm regretting it. Keeping busy.
Only if I've been covering the essential bits of this one. He's been progressing, he's been doing some background performance. So, you know, I've been not running if I can so yeah, it's a sort of, I think that probably makes a triple whammy. So I just feel it's been kind of, but I feel like Harrison's slowly getting into the kind of legends, you know, signatures, just comes around.
Yeah.
And so, you know, but that's been quite nice. That's it's interesting. They're taking the whole time. There's probably not been a big organisation in 2015. So they're doing a lot of high-level stuff. So progressively, probably starting to there'll be much, you know, some aspects of function like beginning to be rationalised. Implementation of the next year, because that's the point at which the kind of it's interesting. It's kind of like sensible discussions
The level of conversation was quite dramatic there, and I'm sure that it was all about Dart. And I think we should really start straight away and have a little bit of a discussion, because you don't get any lunch until you've had a discussion. The free lunch comes after you've done some work. If we just sort of get ourselves settled down, and obviously we've had what we've heard this morning so far is the rationale behind the project, the description of the main data sources that have accrued during the 3 years of the project, the initial outcomes of some of the research, the fact that the data is all online and is freely available, the fact that data has been not just freely available but has been used already, and that there is opportunity to mine these data sets for larger questions, I think, in the future. Now, I think that's a pretty good representation of what's happened so far, and I think it's a pretty good summary of the, if you like, of the achievements of the project. But of course, there's plenty of questions that come from what we've been told. You know, let's be honest, there's been errors in some of the methodology. You know, the guys have wept buckets of tears, I can tell you, on occasions throughout 3 years, because there were some mistakes. But like with all methodological research, you know, we expect those. If we don't make mistakes, we really don't progress terribly far. That's the lunch coming in, guys. We've got to get on with this conversation.
Stop talking.
Well, I was going to say, that's the start point. Perhaps I would like to just open up the court for some discussion or some points of clarification. Who would like to kick us off? Okay, thank you.
Can I ask?
Can you say your name, please?
Keith May from English Heritage. Can I ask Ben a very basic question? You contrasted the two probes in terms of the encode probes.
Yeah, the
drill being behind the section of the
right, so they drilled in
section.
close to, not exactly on the section, they drilled sort of like I think a couple of 2, 3 meters away maybe.
Yeah, so they're straight in.
They're straight down, they go straight boreholes, so we get a standard sort of like percussion, go to TT and hammer at the core end, and then you put a plastic tube on, and the probe goes into that, goes through the plastic tube.
So basically, the simple question: does the fact that they went straight to the soil account? You talk about the drying out process in the trench, and that is simply.
Yes, obviously you don't see the same settling properly. I think possibly they create other problems sometimes. I have seen a few instances of water just going instantaneously down, but I think it's possible the tube does create a slight differential flash rate. It's not a good effect, but I think you can do the best you can. And I think every method's going to have a problem.
Okay, thank you.
Certainly that was a point of discussion really at the very first workshop. I seem to remember that came up in terms of, you know, digging a trench, you know, how much will this affect the results, and ironically it probably hasn't affected the geophysical results, which was the thing that we particularly were concerned about, but it did affect the in situ measurements, which we weren't quite as aware of.
There's uncertainties in the meaning of your CDR and resistance data. Have you done lab calibrations of the CDR against the dielectric permittivity and conductivity using samples in the lab against water content?
I've done some work on the TDR permittivity and conductivity against moisture content.
For the different soils?
For the Diddington ones, I haven't done.
What did it teach you?
I don't know yet. I'm still looking at it. I'm still finishing it. Actually, I've got one more. I really need to do a couple more samples with. But yeah, it's work in progress.
But I think one should also say, as a part reply to this, that obviously the TDR sensors that have been initially calibrated against standardized sets of data.
Oh yeah, no, sorry, right.
The conductivity and the permittivity that we get out of our TDR sensors are calibrated by us. And that is important because obviously when we say the input data are different, then we know that our data have been calibrated.
Yeah, so we've calibrated it to potassium chloride solutions for conductivity. I could talk to you more about the methodology, but I don't really want to bore everyone.
As a general point, can people try to articulate loudly and clearly, because the microphones aren't great, and it would be good if we could, catch as much as possible.
Was there any, Paul Corders, was there any application for farming activities such as fertiliser application during the process, and did you see any effect in your data?
Yes. So at the airport data, the sites in Herne Hill and Gloucestershire are organic. So there's no fertiliser application there. But at Diddington, you can see certain tractors turning around at the end of the field, and you have kind of increased stress and bigger variations there.
One of the useful things from Herne Hill as well, and I'm not sure if it came across clearly in the slides, is that a quarry field, there's a number of different crop trial areas where they're looking at different ploughing and drilling techniques. And so, it's against the same thing. We can benefit from the fact that they're running different in situ trials, and you can see the impact that's having on both the topographic and crop response with the data that we're getting.
So it's too small to see in for instance, conductivity data?
Those areas
weren't covered, so we
okay.
Can you remember off the top of your head, Toby, how wide those strips are?
All right, that's not my field, but I will make the comment that the cherry copse setup was in one of your pictures. Pigs are up to one side. Last time,
the pigs moved.
The middle of a swamp, basically. It was dead by then. But if you were thinking about the fertiliser application and the conductivity changing due to the nutrients moving down through the soil, that'd be a very interesting model, but you'd have to go to someone like Cranfield to be able to explain that one.
Actually, that's one less parameter that we've had to think about, actually, which is actually quite a good thing, because it allows us to get a better handle on the archaeological solutions.
There is actually literature about surface wetting. So, Anne Rosemary. There is a whole load of stuff now being published through the European Journal of Soil Science and other places to do with what happens with surface wetting and rainfall when you've got sludge applied, fertiliser applied, things like this. So it's something we want to know more about in the next few years, I'm sure.
Hi, I'm Kat Otterlow, Central England, so it's going to be from a farming perspective, I guess. I was just wanting to know, when you selected your test sites, how much you looked into past farming practice. Obviously the one that's at an agricultural college will have a lot more knowledge about, but you can actually look further back than that using the Dudley Stamp land use inventory, so that you can see the 19th century usage, and you may find that your water permeability issues are to do with subsoiling. If they've broken a pan, you'll be getting completely different permeability.
I think probably the short, I would just put a short answer in first of all before you give the long one. Had we had a more complete history, then we probably wouldn't have had a ditch with paint.
It wasn't part of the criteria. Primarily, we needed to get sites we could get access to, and that was the major constraint. RAU were more than forthcoming, and it's been a wonderful partnership working with them. And Frontal Estates at Diddington, it was mainly due to Quinton Carroll, the county archaeologist, basically pointing us in the direction of what he considered would be amenable landowners. So, we had our broad criteria of making sure that we had heavy soils and free draining soils within close proximity, so that logistically we could actually do a reasonable amount of work within a reasonable time frame, and then everything else, was a secondary and tertiary concept.
If anybody else has got that problem, we've got some amenable landowners, so if you can speak to Natural England HE advisors, we can help
Fantastic. Thank you.
Dave Cowley. I was just running on from that point. I think it is turning the point on its head and thinking about the issues of how do you outscale the results from the DART project, how do you extend those into wider landscapes. I think this kind of consideration, characterization probably of historic land use, 20th century, 19th century, so on, is going to be absolutely crucial. It's an aspect of that landscape character that will determine whether or not particular result, or maybe a factor in determining how extensively you can start working out the results of the DART. So, sorry, that was into incoherence. I hope everybody got the sense of what I was trying to say. Apart from Chris, who's obtuse.
Thank you.
I think you're right. Scaling this up has always been a problem. We have lots of data about 4 small holes in the UK, and that is in no respect representative of pretty much anything else apart from 4 small holes in the UK. But it has also provided us with this broader network of people who are adding in this kind of insights. We're working with Toby, who's got more access to some of the automated data which is collected as part of the day-to-day agricultural process. We can now start to potentially feed that into broader models and look at ways in which we can extrapolate this to broader scales.
Bob Evans, in relation to that last question, in fact there are soil maps which will help you to extrapolate enormously. I mean, you've actually sampled the biggest national soil map unit in the country, which is on Jockey Boulder Clay. It covers 2.4% of, I think it is, something like that, with Lowland England, no, in fact all of England and Wales. There are ways of extrapolating, they might not be very statistically sound or anything like that, but the kind of sites you've looked at, they cover soils which are roughly similar for large chunks of the country. Would have no problems in extrapolating from where you worked, and that's why it's interesting what you've done.
Yeah, I think that I also follow on with by saying, actually what we have done, we've created benchmarks here. Of course they will be different if you go to different places, but we've actually created a framework around which other people could very easily do similar projects, not necessarily doing all the monitoring, but doing the seasonality type experiments. So I think that's. I think we should look at it in a reasonably positive way. I think. Any other?
Slightly negative. Is that?
I'm being negative.
I'm just I'm just worried that the last 3 years, unfortunately, have not been representative.
Yes. Wait for the next 3 years.
We don't know that yet.
But that's not the point, though. The point is,
if you want to extrapolate.
No, absolutely not. Because we've seen highs and lows within that time. It's just that they haven't actually coincided with our concepts of the seasons. Okay? So it doesn't matter.
But they've broken records because we've had the wettest summers for 2 years in a row. We've had the driest winter for about 30 years. We've had just had the hottest summer. So it's difficult to. You can still extrapolate. But you can't say that you might see the same results if you do it again in a more normal year.
Is that not actually useful though, because you've got that drought cut-off point on some of the data, which you wouldn't normally have seen or known to expect if you haven't had extreme weather?
Totally not true from where I come from university. This spring I resigned as greenhouse gas coordinator for DEFRA. We're trying to develop a national inventory for nitrous oxide emissions, methane emissions, obviously soil measurement of nitrous oxide emissions. And yes, we have had some interesting weather events, but they actually tend to the norm. And if you look for the presentations from the greenhouse gas, you'll see the analysis. Okay, you've only got 2 sites in greenhouse gas, we have 15 around the country. But when you started mapping the whole thing together, this has not been an extreme period. It's just been, we feel it's different, the media expect it to be different, but actually it's not that far off the norm.
to add there is that we're also in the process, have been in the process of handing over the equipment to the Agricultural University. I take your broad point there, Jen. What we ideally want to do is to start to get some longitudinal monitoring, some longitudinal data. And so we're building that relationship with Toby. Watch this space, basically.
I was just going to add to it, that's the point about understanding the mechanisms within the soil that produce the detectable effects that we're detecting in the ground surface, whatever the weather conditions are. If we can predict, at least to a reasonable degree, approximation, what the geophysical outcomes or detectable outcomes of a particular set of conditions will be for a particular kind of structure in a particular kind of soil, it doesn't matter if they're extreme, as long as they're reasonably reliable. And the problem then is getting to that reliability.
Sue Starr-Rouse, English Heritage. I hope this isn't jumping the gun before the discussion about curatorial impact. But what I've got from this morning is how very variable things are, both within a site over time and between sites and different weather events. Most archaeology in this country is undertaken because of developer planning regulations. A local authority curator can stipulate that there is a planning condition for a geophysical survey. The timing of that geophysical survey cannot be held until the optimum 1 month after whatever the best conditions would be.
Yeah.
So where do we go from here?
Well, I think you have jumped the gun on that one. I'm sure that we will talk more about this, but I think that you're right. That we've actually, part of the issue here is that people have, the curatorial side have not specified earth resistance as a main way of investigating areas of proposed development because of this seasonality issue. And I think what Rob's proved, well, he's illustrated that if we look at it in the traditional sense, that's actually quite a good call. Actually, in fact, we're not using earth resistance as a primary focus. However, in amongst all that data, there were other little bits there that were tending, giving us some ideas about opening up some other avenues. Okay, and I will actually say a few more words about that this afternoon.
Are you wanting to start that discussion, or hold it for the side?
I'm going to hold it if possible, actually. If that's okay. Otherwise, I'll have nothing to say this afternoon. But that may be a good thing. So somebody please ask something else, because otherwise we're going to have to go back on that one.
Can I come in more generally, Roger Palmer? What you're leading into or avoiding is any discussion of an afterlife for darts. Are you expecting extrapolations to be made by the data mining, or is there an intention to carry on internally, as it were, in the ways in which you want to go?
Do you want me to?
I think you better.
We still have 3 PhDs to finish off and write up, so there's work that's going to be finalised from that. I still am going to be looking at the data, and the data is out there. I think you're really referring to, is there going to be any formally funded work that is going to close that particular gap? At the moment, it's unlikely. We have a follow-on fund application, which will hopefully be submitted relatively soon, but the stipulation of the follow-on fund is not to undertake research as a primary objective. And so that would be about reuse of these kind of resources within the community and a variety of other affiliated actions. So as a research call, it's not a research element. The other problem is that funding is now becoming increasingly difficult. So it does need more work into it. And we knew that from a very early stage, which is one of the reasons why we focused it on having it as an open project. But the landscape is a landscape. And if there's no funding available, even if it was available, it's still now very complex.
Not so much a question, just in relation to the comments about commercial archaeology and timing of access. I'm John Wells from West Lothian Archaeology. The important thing about the DART project and identifying these times is that it's really useful to community groups, because community groups can get out to their sites, whether it's with soil resistance and those that are lucky enough to have radiometers, magnetometry, or more importantly, the growing use of personal aerial photography, whether it's UAV or hopefully more kite aerial photography. So, wonderful as far as community groups go, and obviously we'll be discussing this in more detail this afternoon.
In response to that, saying that one of the things we need is a lot more data. We need to be following change within soil moisture, within archaeological features, and the effects of that on geophysical characteristics. And if local community groups can, with their long time scales and their regular access to sites, instead of going back to a site once because that's your own commercial opportunity to do so, get us more data, get us more continuity. That sounds wonderful.
And this is what we do within West Lothian. We go back to each site year after year and throughout the year as well, from usually from the visible to the thermal infrared.
Is there a mechanism to set something like that up?
There should be.
Because you need the ground measurements to go with the photos, don't you?
We need the soil data.
We have got that in as part of the follow-on fund in looking. Well, the umbrella element of that is trying to increase engagement by the geophysical community to deposit their data in the ADS or through our portal. But it's really trying to look at some of the softer issues surrounding why data is not being shared more readily by the community, because until we start to get to a stage where we can integrate a broader spectrum of both geophysical surveys and surrounding subsurface measurements, we won't be able to do these things with data. It's just important.
You need a probes kit for everybody, right? John's got kites kits for everybody.
Using Arduino or Raspberry Pi or other small-scale systems is now more than achievable. It's not just the fact it's achievable; it's affordable. And there's a number of open hacking communities that are based around building around soil moisture and small-scale temperature devices, which are essentially autonomous.
The raw data is available as open data, is it?
Oh, absolutely.
Presumably, it's open inverted commas in as much as if you do survey GSSI, it's in GSSI data format, so you really need their tools to look at it.
It's in broadly interoperable open formats. All the geophysics data is in text, and yeah.
So that's true of radar data?
The radar data we haven't done the processing.
And radar data will be available as SIG-Y and as raw data. So basically, all our data, read the guide. All our data are available both in the proprietary format, which they were collected in, such that if you have the software, you can go directly into the data. And they are also interchangeable formats, such that you can convert it using your own tools into whatever you use.
The focus on that was to maintain the integrity of the data as close to sensor and sensor collection as possible, because any subsequent process, if you're exporting it from a proprietary environment, tends to be black box, and you don't know if it's throwing stuff away. So we're trying to maintain basically data integrity from source through to reuse.
Keith May again, just picking up on the data side, and something Ant you said in your presentation, which was great, about using the open data. And you had the phrase accessible URI, and I'm just wondering, does that, by that, do you also mean persistent URI, or do you mean something? If you mean something else, can you just expand?
Accessible in the fact that it's resolvable under any circumstance, i.e., it's not behind either a login or a paywall.
Okay,
so it's there.
At what level of sort of granularity are you putting them out? Are they each data object? Did you say the photo has its own URI?
The photo has its own URI.
Thank you.
Yeah. And it's citable. We have it as a BibTeX citable reference for each of those objects. So you can cite the data at a collection level or at an object level if you so desire. Also, your other question is a persistent URI. It's not persistent. We don't have that facility. We're not ADS. The point of the repository was to realise the goals or to address the needs of the project. So persistence is a long-term commitment.
But to follow up their needs, if some of it's going to ADS and they are now doing persistent URIs and some of our stuff, so it would be interesting to look at what data would be worth having as persistent URIs.
Yeah, I mean we have that data, we have that server available to 2015 as a start. And we are also looking at getting DOIs for data as well, so I'm working with leads on that. So ultimately when that data is moved to a place that has greater persistence, the DOI should be the major referencing node. So that, as long as you have a brokering service, the DOI should point to that extant data. If that makes sense. Sorry if I put jargon you do.
It's jargon, but I'll talk to you more. I'll talk to you more about that as well. Thanks.
Has got any more points they'd like to make? Chair on the project.
Yes. I know that you couldn't talk about the soil analysis, but how has been incorporated all the data from the soil analysis for each of the different PhDs? Has it been, should I ask?
Ask that.
How has been the incorporation of the soil analysis for each of your PhDs?
So far, because the way this sort of whole project has worked, all the PhDs have sort of been their own separate research, and we actually haven't incorporated the actual soil analysis to each strand yet. I mean, Dan might have a bit more information.
Laura and I are kind of talking about it, I suppose.
Yeah.
But
it will happen.
Yes, it will. It will happen.
So you've got these data sets that
Yeah,
are
a
ready
low
for
stage
you to be used,
well, yeah.
whatever.
And the source data is
Source data,
it's all on.
half of it should be there already, and the other half should be fairly soon in the repository.
Is available to language
the other side of the soils data is that we've taken two broad conceptual approaches, which is to look at it from a geoarchaeological perspective from Keith, and then to look at it from a soil engineering perspective from Laura. And so that we can start to see where there is a correlation between how each domain starts to both conceptualize and represent soils, because it's really been done before from an archaeological point of view. So it gives them a better position to start to reuse kind of a macro soil approaches, which are larger, cover more of a country, and will make it and will allow us to model these kind of responses on a national basis. So.
Should really have said that Laura's the fourth person in this student's list, and who's actually sort of sat outside of DART in terms of the funding, but has actually undertaken a lot of work on the material during this period. I think that the question amply illustrates really what Dave was saying earlier on. There's this. What we need to do is the idea of fusing these different strands more effectively. In terms of the students' own personal points of view, they have PhDs to get. It's not about integrating all of the data sets in each and every PhD, but the outcome can only get better as we progress with this project and we actually come to the the final conclusions. So I think we still have a fair way to go in that direction, I think. And of course, it'll only be then that we will actually see this full sweep from inputs into the ground to the final outcomes that we're measuring either on the ground level or indeed more remote. Well, we've actually come to lunch. Unless anybody wants to ask another question and stop us from having lunch, it would be a great time to have something, and then we're back at 4:30. Okay? So
do you want to turn it off over lunch?
I don't know. We don't know what we're going to say.